Hey guys, great job on your 1 proportion and 2 proportion tests. We're going to start sample means testing. Hopefully you'll see that it's a little bit easier, especially when you prove normality and also when you actually use your formula to write your equations. So I'm going to be uploading these handouts in Google Classroom, so I suggest you print them out or take notes on how I'm working these out, so that way you can follow along as I go and as you watch the video. So hopefully these videos are helping you. I'm doing my best. Just give me a break if you're thinking I don't know what I'm doing. So I'm trying. So we're all trying. So let's just hang in there together. The topic is called one sample hypothesis testing. And you know what? We've already built the groundwork for most of this, because when we did the confidence intervals, we already have the bones of what we need to do. So just like confidence intervals, there's kind of 2 versions. When you read information about a mean, remember a mean, you've got a mu. No more percentages, no more proportions in this, okay? And so there's 2 versions, because, see, they're going to have to tell you about sigma, the standard deviation. Well, remember, sigma is the population parameter, okay? Now, do they give it to you all the time? No. Sometimes they're not going to give it to you. And so if sigma is known, we call it a z-test. If sigma is not known, then just like that confidence interval, we change z to a t. So it becomes a t-test. Okay, and there's going to be 2 types of t-tests. I mean, you do the same thing, it's just the way the data is presented. So I'll go over both of those here in a second. So you just have to keep it straight. Is sigma known? If sigma is known, then you're going to use a z-test. If sigma is not known, then we're going to use a t-test. Okay, and so I've already loaded up the handout answers. I thought it was a little easier to go through it if I've already kind of sort of written it out. Okay, so the first question I'm going to be doing is 11.1c. And so they're doing a test comparing some scores on the ACT at this particular high school. They call it South High. And over the past, years, they've discovered that the mean has been 20. So 20 represents our mu. Okay, so that's our parameter. That's our mu. And so what they did was, in order to prepare them for the ACT, they did a special prep. Hey, we did something like that. Wasn't it called torch prep? And so here they had 53 seniors. Now this is a key word here. All 53 seniors planning to take the ACT. They enrolled in the course. So the mean of those 53 was a 22.1. All right. So we kind of sort of consider that value right there as our X bar. Okay. And so here, looking at this last sentence, assume the ACT scores for seniors at South High vary normally. That'll come into play a little later, with a standard deviation of 6. Okay, and so here, they are implying that 6 is our sigma. Okay, so just kind of helping you out a little bit. So, this page kind of walks you through the steps, and then eventually you're just going to be give it a question that says, hey, is there enough evidence? Okay, so these are the state plan do's and concludes for you. All right, so here's my stating. So they want to identify the population and the parameter of interest. Okay, and so also state a hypothesis. Well, your population is just all students and seniors at South High that are going to be taking the exam. So the key word there, all students. And then your parameter, I kind of wrote it twice. Your parameter is what your measurement, what mu stands for. So I'm going to come over here and circle that. It says the mean ACT score of students taking the prep course at South High. Okay? And so there's your mu. That's your parameter. And so that's what you're going to be doing before you do your test. You're going to have to identify your parameter. Just like last unit we did P. What does P represent? What does P1 represent? What does P2 represent? So this is the same thing. So then coming up with your hypothesis, they wanted the hypothesis stated in words and symbols. And so remember, our null came from up here. They're claiming that the mean was 20. But you see, they want to show that prep course made a difference. So they're going to say, hey, it's going to be greater than 20. So that's why the alternative was mu greater than 20. Okay, and then this stuff right here, this is just me explaining what that meant in words. Do you have to do that all the time? No. You're used to seeing this section here. Okay, and then we move down to number 2, identify the appropriate statistical procedure and verify conditions. Again, this is understood that you always identify. See, we're getting into different tests. Now we've got several of them under our belt, so you need to let the reader know what the test is called. So we call this a one sample Z test. A Z test, okay, because sigma is known. And you all, the conditions never changed. It's just how you go about maybe talking about normality is it. So simple random sample, well, it really didn't say anything about a simple random sample. They put all seniors, all of the seniors in the program, the prep course. And so we proceed with caution. Population at least 10 times sample size. We're kind of assuming that there are at least 530 students in existence that can take the ACT. Now, not particularly here at this high school, but in generally speaking, there are more than 530 students taking the ACT. Independence is assumed, so each student taking the exam is independent of the next student taking the exam. But when we talk about normality, there's kind of two things. When I read the STEM, remember me underlining the word normally? So it's stated in the prompt. But also, another thing you can do if they didn't say normal is look at your sample size. N was 53. So if they didn't say normality in the prompt, go to the sample size. 53 is indeed greater than or equal to 30. So the central limit theorem is achieved. Okay? So conditions are met, proceed. So then we go into calculating our test statistic and the p-value. So over here to the left, I wrote down some info that's going to come into play. So I wrote down my sample mean, X bar. That was the average after they took the prep course. This was their score now, 22.1. There were 53 students. N was 53. And then remember sigma. I kind of helped you out with that question a little bit because sigma is 6 in that problem. And so notice our formula. I hope you recognize at least this piece right here when I circle it. Maybe. Hello. Pen went off. All right, so this piece right here, hey, that came from the confidence interval. If you know sigma, use sigma. So sigma over the square root of n, that was part of our formula for confidence interval. Well, we use it in the hypothesis test as well. So X bar minus mu divided by sigma over the square root of n. So filling in our numbers, 22.1 X bar minus 20. Well, what was 20? Guys, that was the null. That's P naught. Okay? And then over 6 over the square root of 53. Now, you can go to your calculator and enter in. It's called Z test. So if you go to your calculator and go to tests, It's number 1 on the question. And so you're just going to enter in your stats. So I'm going to enter in 20. Sigma was 6. X bar was 22.1. And N was 53. And I'm going to choose the same direction that the alternative hypothesis was facing. So I'm going to use the the third one over. I want to be greater than. So go to calculate. And I get a z-score of 2.55 rounded. So I'm going to draw my stinking sketch. Some of us are still not doing that. But anyway, the p-value from the calculator was 0.005. And nowhere did they give me an alpha level to use, so I'm going to default to 0.05. And so I'm showing that to the reader right here. And my decision is to reject. I want the p-value to be less than alpha. P-value less than alpha. So yay, I get to reject. So my conclusion is the same. So we have enough evidence to reject the null and state that the mean ACT score of seniors who are taking that prep course will have a mean score greater than 20. Okay, how do I know? The p-value 0.0054 is less than alpha 0.05, so my decision to reject is justified. So basically, guys, there's kind of 2 things that you're doing. You're creating your new z-score, but you've got a brand new standard deviation, but it's not hard. You've seen it before. And then the other thing is you're just the way you talk about normality. And so it's on that screen right there. Normality. How do you prove it? How do you check for it? And so it's way easier. No formula needed. Okay. But remember, in the prompt it said normal. So don't forget, when you're checking for normality, there's 3 things. Did it say it? Just before I change screens here. Did it say it? If it didn't say it, was your n greater or equal to 30? That way you got your central limit theorem coming in. And the last thing is if they give you data. And we'll get to that here in a little bit. If they give you data, then you do a box plot. That's the easiest graph to make to tell if you have a normal distribution or approximately normal, okay? So don't forget about that. All right, so let's move on to a different question. Well, the different question is what you think it is. The other top, sigma, not known. And so I'm over to 12.1b. So flip over to that when you get your handouts. And here we're doing a little bit of environmental work here. Amount of lead in a certain type of soil when released by a standard extraction method averages 86 parts per million. Okay, so when I read that, they've got to give me a mu. So guess what? 86 is my mu. And then they do this method, and it's tried on 40 specimens. So that's how many is in the sample. And this is what it yields, 83 parts per million. So 83 is my X bar. And then they tell me a standard deviation of 10. Now, wait a minute. Where'd that 10 come from? Well, 10 came from the 40 specimens. Okay, so this time, this is not sigma. 10 is not sigma. 10 is sample standard deviation. So he is my SX, the sample standard deviation. Okay, can you see the difference? So you have to read the prompt and understand where the numbers belong. Okay, and so this is one where they just say, all right, is there significant evidence at the 5% level? Well, what they mean? Well, alpha is 0.05. That's what they're saying. That's a significance level. So they want to check it, test it against 5%. So that the new method frees less lead from the soil. So is this a better method? Okay, and so here, just identifying the parameters. So step 1, state, state, mu is equal to the mean lead content of all soil released using this new extraction method. You have to identify mu. And then I set up my null and alternative. So mu is equal to 86. The null is always equal to the parameter. Mu equals 86. And then this statement here told me what my alternative was supposed to be. Mu less than 86. They wanted to see if this extraction method made an improvement on extracting the amount of lead. Okay, and so what was my procedure? One sample, no longer do I know sigma, so now I change it to a t-test. One sample t-test, so that's your name. And then over here, I just made some notes. And then one thing I involved new, because remember with the t-test, I'm not using z anymore. I have to go to my degree of freedom. Degree of freedom means n minus 1, so degree of freedom is 39. Okay, so simple random sample, when I get into the planning, wasn't stated, proceed with caution. Population at least 10 times sample size, 10 times 40, at least 40 possible soil samples in existence. Independence is assumed, and then 40 is greater than 30, so to check for normality, central limit theorem kicks in. So I get into my test statistic. So t is equal to 83 minus 86, x bar minus mu, divided by 10. 10 was the standard deviation of that sample over the square root of 40. Okay, and so again, calculator, you can go straight to it and enter in your information. This is the second option. And it's still the same information. You're going to enter in your mu, your x bar, your sample standard deviation this time, n, and then choose your alternative, and then calculate it. And so when you get to there, it's negative 1.90 is your z-score, and then I got a p-value of 0.033. Well, comparing 0.033 to alpha, 0.05, yes, it was indeed smaller than 0.05, so I get to reject it. So don't forget my sketch. And so, conclusion, we have enough evidence to reject the null and conclude the mean lead content of the soil using that new extraction method is less than 86 parts per million. And I just justified the p-value was less than 0.05, so that's why I get to reject it. Okay? So hopefully not too much confusion on any of that. Not today, but I'm going to tell you why degree of freedom will come into play. Okay? Because later on I'll give you a couple of hints on why degree of freedom may come into play with a hypothesis test when I want to just answer what is the area here without having to work the whole problem. Okay, so that's later on. So there is a reason why degree of freedom will be involved. Okay, last example. This is one where I actually have data. And the data is a comparison. And the whole deal was, did I make an improvement? So here they're just running a test on, does too much sleep impair intellectual performance? Well, you know, sometimes you get way too much sleep. And so researchers examine this belief by comparing performance of subjects in the morning following 2 normal nights sleep and then 2 nights of extended sleep. So notice, they've numbered the subjects. So here's subject 1. Now notice subject 1 had normal night sleep, and then subject 1 also had extended night sleep. Guys, this is a matched pairs experiment where the subject goes through both treatments. And so similar to what we talked about in confidence intervals, I want to know, did the difference make a difference? Does that make sense? And so here, we just want to know, does extended, play a role? And so how did they do this? Well, in the morning, they were given a number of tests for their ability to think quickly and clearly. So one test was for vigilance, where the lower the score, you got to understand it, the more vigilant, and the higher the score, the less vigilant. Vigilant is alert. So the lower the number, the better. The higher the number, the worse you did. Okay? And so we're trying to show that extended minus normal, we wanted to show that these ended up being, these ended up being, I lost the page. Sorry about that, I lost my page. That these numbers for extended were higher than the numbers for normal. And so if I did extended minus normal, then I'm hoping to have positive results. Okay, but positive results means that extended sleep did impair. All right, and so basically I have to get a difference. So this is what I did. Notice I put list 1 next to the word normal, list 2 next to the word extended. So this is how I found the difference. I stored all of the normal scores into list 1, all of the extended scores into list 2, and then I did in list 3, I did L2 minus L1 and got these numbers. So this is actually all of the numbers that came out of list 3 right there. That's list 3. And then I did a 1-var stats on the entire list 3. Make sure you're doing the right list 3. And so that was able to give me an overall difference. So I'll get to that here in a second. And so here, number 1 takes us back to chapter 5. If this experiment was properly designed, explain how the assignment of subjects to treatment could have been carried out. Remember, each subject should go through both sleep treatments. And so this is where you're trying to let them randomly be assigned to groups. So you can use a coin toss, something like that. And so subjects should all be tested and are both conditioned, but randomly assigned to each of the 2 groups. Heads, if you flip a coin, heads means 2 nights of normal sleep followed by extended sleep. And then extended sleep first, then normal was the other group. And so allow for a break in between to avoid any impairments. So you don't want to do this back to back to back to back nights. So you might want to wait a week and do another and see what happened. Okay, but you have to show how you randomized right there. That's a key word, how you assigned them. All right, so then the second thing we did was number 2, carry out the test. So here's carrying out the test. So you have to tell the reader what the mean was. Well, what does mu stand for? Well, mu is your mean difference in vigilance score. So this is what we're focusing on, extended minus normal. All right, and so I'm hoping to have positive scores, that extended scores were higher. All right, and so you were less vigilant, if you will. You were not as alert. And so here, the null, now I did a subscript, that's a mu of D. If you can't read that, that's mu of D, meaning the mean of the difference. So why do we choose 0? Mean of the difference is 0. Well, we're saying that there's no difference. So that's why we're letting the difference be 0. But you see, we want to show that there's a positive difference, that extended sleep is higher. So we want to show a positive difference. So that's why I said the difference was greater than 0 as my alternative. Procedure, 1 sample, t-test, but the key word you need to also include now is paired, because it's a matched pairs scenario. I'm going through all my planning stage, just checking. So simple random sample, not randomly selected, but randomly assigned. That's a difference. They were assigned to groups, but the people themselves weren't randomly selected. So flag it, proceed with caution, keep going. There's at least 100 subjects in existence. Independence is assumed between each volunteer or person that we're using. And then normality, this is where we're using a box plot. So where's the data? It's list 3. So do a box plot on list 3. That way you can tell the shape. Now, as long as you don't have extreme outliers, you can have a little bit of skew. Tell the reader what you see, okay? And so mine says box plot of differences shows approximately normal, no outliers, proceed. Okay, and then I just jotted down from OneVerStats this information. The mean difference was 3.8. So it was a positive difference, but was it significant enough? Is it far enough away from 0 to make to be significant? And then I copied down my standard deviation. And so now I proceed to my test statistic. And so 3.8, and remember, there's the null hypothesis. This is P naught, 0, divided by, and then 4.66 over square root of 10. So I got a z-score 2.58. There's my sketch, and 0.015 was my p-value. Again, this came from just t-test, from the calculator, just like the last problem. It is less than 0.05, reject. We have enough evidence to reject the null, conclude that there is a difference between scores among extended sleep versus normal sleep. So it appears extended sleep does impair vigilance or alertness. So how do I know? P-value of my 0.015 is less than 0.05. So my decision to reject is justified. So 3 types: sigma known, sigma not known. See if you can tell the difference when you read the stem of the question. Just follow the same steps: state, plan, do, conclude. Your formula right here, especially for a difference, you're always using 0 for your difference, always, when you're doing a matched pairs, okay? And then again, checking for normality, but the rest of the stuff you've been doing, okay? So good luck with this assignment, and I'll upload what ones I want you to try, and please ask questions if you need to, all right? I hope this helped. Have a great day, okay? Bye.